All right. So a couple weeks ago, my son was telling me of some stuff he was doing with ChatGPT, and he's like, hey, did you know that you could have ChatGPT impersonate a famous person and answer your questions as a famous person? I was like, no, that sounds really cool. He says, yeah, you want to do it with you? And I laughed and I said, son, I'm not famous. He's like, well, let's try it out. And so he asked ChatGPT to impersonate me. And it knew who I was. I was both terrified and flattered. And by the way, one of my bucket list items is to have a Wikipedia entry. This is close. So yeah, it's pretty cool. So with that, I thought it would be interesting to feed ChatGPT questions from my students and ask it to answer as me and compare it to what I would actually say. Sounds like fun. Let's do it. But first, the prompt. For the next several questions, I want you to answer as Dustin Fife, the creator of the YouTube channel Quant Psych. Let's see what it says. Considering impersonation limits. All right, I'll channel my inner Dustin Fife from Quant Psych. Fire away with your questions. I'll do my best to provide the insights you're looking for. Good start. Seems like a friendly dude. First question from a user. And by the way, these questions are pulled from my online, on-demand Intro to Simplistics course. So if you want to sign up, do it. I'll leave a link in the description. All right. When interpreting scatter plots, how can we distinguish between meaningful nonlinearity in a relationship and random noise? And what steps can we take to validate whether a lowest curve or another model better represents the underlying trend? I don't know if I should answer the question first or let ChatGPT say it. I'm going to start with ChatGPT and maybe we'll vary it up. Okay, we have an answer. When eyeballing a scatter plot, the key is to ask, does that bend or curve hold up under scrutiny, or is it just random scatter we sometimes expect? Here's how I break it down. Distinguishing meaningful nonlinearity from noise. Visual pattern and consistency. Start by visually inspecting your scatter plot. If you see a consistent trend, say a gentle curve that seems to persist across different sections of your data, that's a hint there. Might be genuine nonlinearity, but if the apparent partition only shows up in a few isolated areas, it could be noise. I would agree with AI version of myself with the added thing is that what happens with lowest lines is they tend to tick up at the end because they're super sensitive to outliers, and outliers happen in the tails of a distribution. So you might get something that looks pretty flat and then at the very end it pops up. Is that real nonlinearity? Well, probably not. It's probably just catching an outlier. So good job, ChatGPT-ish. Residual analysis. After fitting a simple linear model, check the residuals. What? If you observe systematic patterns like a curve... Oh, okay, never mind. In the residual plot, that suggests your linear model isn't capturing something, possibly a nonlinear trend. Random noise, on the other hand, should result in a residual that looks randomly scattered around zero. So, yeah, that's another thing that I might do. Let me look at the original question here. How can we distinguish between meaningful nonlinearity in a relationship and random noise? I think I disagree with that one. Because whether you residualize it or not, random noise is going to play the same role. So, no, I don't think a residual analysis is going to do it. It might make things more apparent. So maybe I could buy that, but probably not. Statistical testing?
No! No! What the hell is wrong with you?
I feel absolutely violated. Violated! Well, let me read it first. Tools like the Ramsey reset test or tests for nonlinearity can help formally assess whether deviations from are statistically significant. Ugh. Why would you suggest I research statistical significance? Let me look up something, though. Ramsey reset test? Regression equation specification test. So there is one caveat that I might say this is an okay answer, depending on what this is. It tests whether nonlinear combinations. The Ramsey test then tests whether has any power explain y. This is actually by and then tests whether gamma 1 through gamma 1 through k are 0. Okay. No, I would not. I didn't even know what a Ramsey test was. So clearly, I would not say that. And I am not at all okay with doing the idea of calculating statistical significance. However, what I might suggest, and this would actually be in my answer, is if you suspect there's a bend, I would try to, instead of having the default method, which is lowest, instead of doing a default method, I would do method equals quadratic, because that's less sensitive to outliers. And then I might actually fit a full and a reduced model. So I do a model comparison, not a statistical test, although a model comparison is kind of a test. And then I would use AIC, BIC, Bayes factor, and all those things to evaluate whether that bend in the data should remain there. All right, validating the model, lowest versus polynomial regression. Okay. Let's see where this goes. Loess, flexibility. Loess is great for capturing complex local patterns without assuming a specific form of the relationship. Yep. Smoothing parameter, choice of span is critical. Okay, so it's just explaining the difference between polynomial. Okay. So ChatGPT is answering the question that the user asks. Unfortunately, the user has a misunderstanding of what a lowest line, the purpose of a lowest line. So I wouldn't even answer that question. I would instead clarify the purpose of a lowest line. So what a lowest line is doing is it's trying to give you an indication of what the trend of the data looks like. It's not there for modeling. You use the lowest line to identify the appropriate model to use. So if you see a consistent bend in the lowest line, that tells you, okay, I should probably fit some sort of nonlinear pattern here. But it is not the final model. It is a pit stop to helping you decide the final model. So it's not a choice of, do I use lowest or do I use polynomial regression in my model? You never use lowest in your model. You only use parametric models, at least the way that I teach it. So let's see, bring it all together. In practice, I often start with a lowest curve to get an intuitive feel for any nonlinear trends. Yes, that is true. Then I'll experiment with polynomial regression, carefully tuning the degree via cross-validation and comparing, and comparing the model's diagnostic metrics and residuals to ensure that any observed nonlinearity is robust. What? Then I'll experiment. No, I will choose polynomial regression if I'm unsure whether that curve is bending just because of some outliers, because polynomial regression is less sensitive to outliers. But again, that's just for the visual. That is not for the model building. And all those visuals are there to help me figure out what kind of model I'm going to use. Combining visual insights with formal model validation techniques helps guard against mistaking random fluctuations for meaningful structure. Yeah, not something that I would typically say, but yeah. Remember, it's all about balancing model complexity with interpretability. Always be cautious of overfitting and lean on both graphical and statistical tools to make your call. I agree with that. All right, so far ChatGPT is not doing very good. I feel like I should give it some feedback, but maybe later. All right, this time I'm going to answer the question first and then see what ChatGPT says. So this question, user is asking, I suppose this is both for bivariate and univariate models. When visualizing a data set that is not entirely familiar, how do you make decisions on which variables to visualize? Understandably, if it's a relatively small data set, variable-wise, no problem, do it for all. However, I often work with data sets with 500 plus variables. Physician researchers, am I right? Yeah, you are. Having worked with physicians, yes. They like their variables. And I've gotten close to crying myself to sleep at night after reviewing 1/20th of the visuals. My first response would be to give you a hug. I'm sorry this is causing you sleepless nights. But I empathize. All right, so before I figure out what ChatGPT is going to say, what I would say is if you are, don't visualize all of those variables, because all of those variables, very few of them might be actually important. So in those situations, unless you have a specific hypothesis in mind in advance, so like it's very common for doctors and medical and biological researchers to have a specific research question in mind, and so they will collect the variables that they need for their research question. But they're saying, well, I've already got this blood, I might as well collect information on these other biomarkers, and so they get like hundreds more. But if you are doing a targeted hypothesis, just visualize the variables that are part of your targeted hypothesis. If you are fully in exploratory mode, then what I would do is I would use a variable selection algorithm, like using random forests, either vsurf or with variable partitions, which I can leave a link to that strategy in the description. And so the purpose of that algorithm will be to winnow down the list of variables substantially to only the variables that are meaningful enough to look at. And then you might end up with like 4 or 5 variables. And then that's way easier than visualizing hundreds of variables. Now, let's see what ChatGPT has to say. All right, when faced with high-dimensional data sets, I've learned that you can't simply eyeball every variable or pairwise relationship. No duh. Here's my strategy. How confident you are about what my strategy is. Leverage domain knowledge and automated summaries. Before diving into the sea of visuals. Sea of visuals? Ask yourself, which variables make theoretical or practical sense given what you know? Often physician researchers have an inkling about which clinical or biological markers might be most useful. That's a good insight, yeah. Use that as a starting filter for a systematic approach. Generate automated summary statistics. Look at distributions, missingness, variance, and skewness. Tools that automatically flag unusual distributions or high variance can save you hours. That's not something I would recommend. I'm not a fan of summary statistics for like univariate distributions. Like, who cares what the mean and the median and the mode are? You need to visualize it to, like, the mean only makes sense if you have a symmetrical distribution. And so why start by looking at the mean? Why not look at the visual first and then say, okay, and you don't even need the mean. You can just look at the distribution and say, oh, it seems to be centered around this value. So I wouldn't do that. And then use statistical screening methods. When dealing with hundreds of variables, it helps to compute correlations, mutual information, or other metrics that gauge variable importance. What? Mutual information? What is mutual to help? It helps to compute correlations, mutual information. What is mutual information? Okay, I'm going to ask. What is mutual information? Is a concept from information theory that measures how much knowing one variable reduces uncertainty about another. So obviously I don't even know about that, so I wouldn't suggest that. But mentally noted to look that up later. A correlation matrix or heat map can reveal clusters of highly related variables. By clustering these, you can then pick representative variables for further, more detailed exploration. You know, that's something that I used to do. I used to do a lot of clustering algorithms to try to figure out how variables combine. And I don't do that as much anymore, mostly because why? Why don't I do that anymore? Because that's kind of asking a different question. Like if you're interested in seeing how different variables cluster together, that's really cool. That's a good research question to ask. In which case, like a correlation matrix, there's a way to sort a correlation matrix. I can't remember what it's called, but you can kind of sort it by groupings, or a heat map, or some sort of clustering algorithm like t-SNE or multidimensional scaling might help you pick clusters of variables that tend to vary together. But I don't do that very often now. Dimensionality reduction techniques. Methods like PCA or factor analysis allow you to see underlying structure in the data. Rather than plotting every variable, visualizing the principal components or factor loadings can highlight the main axes of variation and guide you on which variables are driving the trends. No, I wouldn't recommend that. So it sounds like... So I did PCA as an undergraduate when I was taking one of my first intro stats classes. They talked about dealing with multicollinearity, which is its whole other issue, and I've made a video, and I'll link that video below. But doing PCA as kind of a preliminary step for regression, I haven't done that since undergraduate, and I don't like that approach. So it's lumping in factor analysis with there. So I'm assuming this is talking about exploratory factor analysis. So exploratory factor analysis and principal components analysis do a similar thing. Basically, it gives you give it a correlation matrix, and you say, all right, identify latent variables or variables that can't be observed that tend to group these variables together. And it will come up with some algorithm. The problem with these algorithms is they're super prone to capitalizing on chance. And at least within psychology, we've largely moved away from exploratory factor analysis to confirmatory factor analysis. And confirmatory factor analysis, instead of asking the computer to tell you what the structure is, you tell the computer what the structure is and then say, how good am I, based on the data, at capturing the structure? And so I might do that, but and it really depends on the nature of the variables. If you have 500 variables and they're all relatively measuring the same thing, I might actually suggest that. That's actually a good suggestion. I might do data reduction techniques like a confirmatory factor analysis or structural equation modeling or something like that to try to condense that information into one latent variable that you can then use to predict the outcome. So I might do something like that. It depends on the nature of your data. Number 4, automated and interactive visual tools. Consider using interactive dashboards. No, I wouldn't recommend that. That lets you filter and draw down into subsets of the data dynamically. Tools like Shiny in R or Plotly in Python. I don't know about Plotly in Python, but Shiny in R is... Shiny is more a language than a dashboard. But it's a language designed to build dashboards. But Shiny itself isn't a dashboard. So you'd have to find somebody else who's built a Shiny dashboard. And I'm not a big fan of dashboard stuff. I get the feeling that with dashboards, they're one of those things that trick you into thinking that you're learning something when you're actually not. That reminds me of my honors thesis. So when I was graduating, I was aiming to graduate with honors in my program that you could do an honors thesis. And so I was working on a research project and I had a data set, and I should revisit that data set for a video. That'd be fun. I had a data set with like tons and tons of predictor variables, and I wanted to know how like these 7 or 8 predictor variables work together to predict the outcome. And at the time, there was something called GGOBI. I wonder if that's still around. GGOBI. Yeah, Data Visualization System. And so what that would do is it would assert that it could allow you to visualize like 10 dimensions at once. And I was like, wow, that's cool. And even then, I had an interest in data visualization. And so I plotted it. And what it would do is it would like show you 3 dimensions at a time and then rotate. And then once it reached a certain point, if I'm remembering correctly, it would flip one of the axes to show a different variable and then keep rotating and then keep flipping the variable and keep rotating. And so you have this really cool, like, matrix style visualization. And you look at it and you're like, this is so cool. And you feel like you're learning, but you're not. It's really hard to interpret what's going on. And so, unfortunately, our visual pattern recognition systems, although really complex, they're really basically limited to 3 dimensions. So anytime you try to visualize something beyond 3 dimensions, we really suck at it. So the best visuals tend to be very simple. And I feel the same way about these dashboards, that they throw a lot of information at you that are cool to look at, but it's really hard to glean insights from dashboards. Unless you know some stuff about interpreting data from plots, in which case just use regular plots. You don't need a dashboard. Although I would agree with this interactive layer can reduce the initial overwhelm by focusing your attention only on what stands out. So yeah, I guess if your problem is that you're overwhelmed by information, having an easier way to get that information is great, but yeah, that's it. Iterative approach and validation. Start broad. Use automated tools to highlight hot spots in your data. Once you have candidate variables or clusters, dive deeper with bivariate scatter plots or other more detailed visuals. This initial iterative process helps ensure you're not missing critical relationships. No, I wouldn't. No. I mean, automated tools, unless you count like random forest, a variable selection strategy. So one of the big problems with all these recommendations is, not all of them, but a lot of these recommendations is they keep talking about like univariate and bivariate plots. You know, like dive deeper with bivariate scatter plots. The problem is if you've got a very complex system that has like 5 or 6 variables that are interacting with one another, and you're trying to visualize bivariate relationships, you are going to completely miss that bivariate nature of the relationship. You might have a very biased visual representation of what's actually going on. So I don't recommend bivariate visuals at all. I would recommend doing a machine learning algorithm like random forest that will, in the process, account for the multivariate nature of the data and then give you an end result that you can then start to visualize the smaller subset of variables. Ultimately, when working with 500 plus variables, it's about balancing automation with informed decision making. By using summary statistics, nope. Clustering, Dimensionality reduction, maybe. Depends on the nature of the data. You can systematically narrow down the variables worth a closer look without having to stare at an endless scatter plots that could drive you to tears. Every once in a while, it tries to inject some personality in there. I appreciate that element of my personality is showing. Cool, that was fun. Let's go ahead and do one more. Okay, the next question asks, how can we interpret AVPs or added variable plots in multicollinearity? And what alternative diagnostic tools or transformations do you recommend to understand predictor contributions better? Okay, so this is another one of the questions that the question itself shows a misunderstanding of added variable plots. So a lot of people get super concerned about multicollinearity, and I've made a video about it. Multicollinearity, it's not an assumption of linear models like some people say. Like, we don't need to have completely independent variables to make inferences. So the assumptions like independence, normality, heteroscedasticity, and linearity, all those, the reason why we make those assumptions is because the inferences that we make, either with p-values or with confidence intervals, or if we're in a Bayesian framework with the Bayesian equivalents, all those things assume certain characteristics of our data. And if we violate these assumptions, these 4 assumptions, then that means our inferences are going to be wrong. Now, when you talk about multicollinearity, there's no assumption about multicollinearity. You can have correlated predictors, and it's no big deal. It doesn't affect p-values, it doesn't affect confidence intervals, except that it makes them wider just because there's more uncertainty. But it doesn't bias your inferences. So, with that out of the way, how do we interpret AVPs and multicollinearity? So, it's like AVPs were designed to show you what happens in the absence of multicollinearity. So, to give an overview, multicollinearity means your variables are correlated. And when you've got 2 predictor variables that are correlated with an outcome, it's hard to tell which one of those is contributing to the outcome. So the example that I've used a lot in my videos is if you're looking at wealth as an adult being predicted by how hard somebody works and their socioeconomic status. So we know that somebody's work ethic is going to be correlated with their socioeconomic status. If you grew up in a household that rewarded you for working hard, you probably grew up in a higher socioeconomic status household, as opposed to someone whose parent wasn't there because they were working all the time. They didn't learn those principles. And so it's really hard to disentangle the effect of hard work versus socioeconomic status because they're super correlated. And so what added variable plots do is they subtract out the effect of one variable and use what is remaining to see how well it's correlated with the outcome. So AVPs are specifically designed to subtract out multicollinearity and show the unique contribution of a predictor on an outcome. So let me say that again, but more concisely. Added variable plots are a very good tool to use when you have multicollinearity because they handle the multicollinearity. They subtract out the shared information with the other variable and present the net effect of that variable on the outcome, with the caveat that added variable plots assume that the variables don't interact with one another. If they interact, then you can't use added variable plots. But if they don't interact, then you are completely free to use added variable plots, and that simplifies visualization immensely. Now, let's see what ChatGPT has to say. Multicollinearity really complicates the interpretation of it. Really complicates the interpretation of AVPs. No, it doesn't. Because when predictors share a lot of variance, it's hard to pinpoint which one is really driving the relationship. In a clean world, an AVP shows you the relationship between a predictor and the outcome after accounting for other variables. Yes, that's what it does. That's why it's not a problem for multicollinearity. But if 2 predictors are highly correlated, that clean relationship can be unstable or misleading. I suppose if it's like super correlated, yes. Here's some strategies and diagnostic tools I lean on. No, I don't lean on them. Variable inflation factor. I don't. It's been probably 10 years since I've computed variable inflation factor because, again, it doesn't matter. Regression automatically accounts for multicollinearity. Added variable plots automatically account for multicollinearity. All the tools we use already account for multicollinearity. So I don't worry about it. Examining partial correlations gives you a sense of the isolated relationship between a predictor and the outcome controlling for all others. Yeah, that's true. This can sometimes clarify what the AVP is hinting at. Do you see the contradiction within the sentence? It's saying, yes, you shouldn't use AVPs when you have multicollinearity. And then later it says partial correlations should be used instead. And they clarify what the AVP is hinting at. Seems like a contradiction to me. Partial correlations, you could do them. So partial correlations compute the correlation between a variable and an outcome, subtracting out the effect of other variables. That's fine as long as you meet all the assumptions of the model, and there's no nonlinearity or anything like that. And why not just look at a plot? You could supplement it with a partial correlation, but you could also look at the regression slopes because those account for the multivariate nature of the data. So I don't look at partial correlations anymore. I used to, but I don't anymore because I realized, regression gives those to you. You can get standardized betas, and there's a relationship between standardized regression slopes and partial correlations, and I don't remember exactly what it is, but they're very similar. Regularization techniques. Methods like ridge regression or lasso introduce a penalty for large coefficients. They're great for reducing the sensitivity of estimates in multicollinear settings, helping you identify which predictors are consistently important. I don't use ridge regression or lasso. Those are both like more variable selection strategies, and it's been a long time since I've looked at those, and I don't even remember the details. So that's not something that I would recommend. And you're getting more into variable selection than multicollinearity, so I'm not sure why that's showing up. All right, dimensionality reduction. Sure. Transforming your predictors into orthogonal components. Yeah, you can do that if you want to, but I would only do that if there's like a theoretical reason to do that. Because dimensionality reduction means you are collapsing two variables into one. So if you have two predictors and you think they're measuring the same thing, we collapse them into one. Sure, do that if they are measuring the same thing. But if they're not, that's just a bad idea. Centering and scaling. Sometimes simply centering and scaling the predictors can mitigate multicollinearity, because if you're dealing with interaction terms, particularly... Yeah, and I did some research in this about like 10 years ago. There's some debate about... So basically, the idea is that, let's say you have interaction terms in your model. We suspect that if you have x1, x2, and x1 times x2 in your data set, that x1 times x2 is going to be super correlated with x1. It's going to be super correlated with x2. You're going to have multicollinearity, which, of course, because you used those two variables to create the interaction term. And I seem to remember there's some debate about you can center them, or in other words, convert them into z-scores, and that removes any sort of correlation between them. But I think I remember there's some debate about whether that actually reduces multicollinearity. But this question wasn't even asking about interaction or polynomial terms. So I think that's kind of like opening a can of worms that doesn't need to be opened. Respecification or aggregation. When two or more predictors are extremely collinear, consider whether they can be combined into a composite score. Well, isn't that what dimensionality reduction is doing? This is especially relevant if they're theoretically measuring the same underlying construct, which, yeah, I think that should have been combined with this answer. And I agree. Again, if you have good theoretical reason to combine these predictors, yeah, combine them. In short, while AVPs are a neat exploratory tool... Exploratory? I don't think it's specific to exploratory. You can use them as a confirmatory tool. They're really good at showing what the model found, which is really an exploratory sort of goal. they should be used in conjunction with these diagnostic methods by triangulating insights from VIFs, partial correlate, yeah, I don't like their answer at all. So, that was fun. Not going to lie, part of me was a little worried because one thing I frequently say about taking a class with me is when you take even a self-guided class that you have access to me, that you can ask me questions. And part of me was worried that as I did this ChatGPT dive, that I would find out that ChatGPT was just as good or better than me at answering questions. And I would say absolutely not. It is not. So with that, let me just give my plug. So if you want to take a class with me, either live through Zoom, where you can ask me questions directly, or online, where you can type out questions to me, I invite you to visit simplistics.net, where I just came up with a random forest class / visualization. Really proud of that. It's a good class. So I hope to see you in that. And yeah, I definitely feel less threatened now. So my job is still secure. Yay! All right. Let me know if you have any questions, and I'll see you next time. Peace out.